With one infinite love and wholly beyond thought, beyond qualities, I bow down to thee. That was Vivekananda's way of thanking people. I imitated that. Okay, today we'll learn something about physics, about electricity and magnetism, how they're related, how they're interconnected, how they are transformed, and so and so. So first, something to tell about its history. Electricity and magnetism were thought to be disconnected phenomena before, until I think in the 1600s or sometime, or in the 1700s, a Danish astronomer, not an astronomer, a professor, Hans Christian Oersted. That was a style of writing it. Okay, Hans Christian Oersted discovered that electricity and magnetism were connected, but he did it. When he did it, he experienced that there was a flaw in the previous theory. He wanted to demonstrate that electricity and magnetism were disconnected. So he took a straight wire equipment and say from A to B, it runs and current is in this direction. Okay, so he went on with the compass needle and circulated it around a point. And by Jove, such accidents seldom happen in physics. And he experienced that the compass needle really fluctuates from its normal north position, and the fluctuation is in the direction of the circulation. And there was a rule given by, I think, Ampere, that if we relate thumb of our hand to the direction of the current, then the curl of our fingers give the direction of the magnetic field. So magnetic field are likewise. So this is in this direction. I think you can find it in elementary textbook, but now we'll go further deep, fathoms deep, and centuries later, when Albert Einstein published his seminal papers in about general relativity in 1905, and he, through a very beautiful and very simple experiment, demonstrated that electricity and magnetism are just manifestations of the frame of reference through which we are observing it. So he introduced some coordinates. We know that coordinate geometry was invented, or you must say discovered, by Mr. René Descartes, the great French philosopher, who said that I think, therefore I am. Okay, we will not go into philosophy. Let it be the z-axis, let it be the y-axis, and let it be the x-axis. We'll elongate it, x-axis. And he considered a wire parallel to the z-axis. Okay, we'll name it A, C. Okay, the terminals. We have not used B for we'll preserve it for the magnetic field which goes out of the paper parallel to the XZ plane in the Y direction. Okay, in the Y direction. Y direction is out of the whiteboard. Okay. We have drawn a lot of this. See it pervades all space. We'll consider at least in the space in which we are interested this magnetic field persists. Okay, so what happens here? Here we'll take we'll translate the straight long wire along the x-axis, that is we will move it along the x-axis in the right hand direction. Okay, parallel to the x-axis. So how does the rest go? Everything according to Einstein depended on the frame of reference. So first of all we'll consider the frame of reference with the rest frame of reference. Okay, from the rest frame of reference, what do we see? We'll see that the AC wire is going along the x-axis in this direction, and hence we'll compute what will be the force on an electron in the wire. There are zillions of electrons and protons along the wire, but we considered only electrons because the positive charges do not move, and secondly this we know that these positive charges and negative charges present in that wire cancel each other so precisely that we do not feel we do not experience a field nearby it. So how does all of this thing go? I will give you an example that consider two persons. Let this be me and let this be you. If I had a mere 1% fluctuation in balance of electrons and protons, that means I have 1% electrons more than protons. Similarly, you too also have a 1% more electrons than protons. Then we too will have a repulsive force that will be enough to lift the earth itself. So this is a great thing that these two this magnetic field which is very strong, the electrostatic field which is very strong is balanced. If it would not be balanced, we would never have find out that there will be something called a gravitational force, because that is too weak. Okay, so let's not go deep into this and come to the original matter. What will be the force at rest? The force is given by due to Henrik Anton Lorentz, I think. Yes, it is given by the Lorentz formula. It is Q into E plus V cross B. Okay, good. V cross B. But there is no electric field here, as you know. So E equals to 0 and Q is minus E. Minus E is the charge of an electron. E is 0 plus V cross B. Okay, then it comes out to E times B cross V. So B cross V is something which we can, at least in the directional sense, we can imagine it to be given by the right hand rule. So what is the right hand rule? B is in which direction? B is in this direction, and B is in this direction. So B cross V. So we'll go from here, see, from here to here. So where does the so here to here. So where does the thumb point out? The thumb points in the Z direction. So this will be in positive Z direction. So this will be in positive Z direction. Okay. The magnetic field is in which direction? It is in the positive Y direction, but the force will be in positive Z direction. Force rest will be in positive Z direction. Okay. Here we have vector sign. Now we'll continue to see the same matter in another aspect. Now we'll consider another inertial frame. Remember, inertial frame. Inertial frames are those frames in which Newton's laws are valid. So we'll consider the frame which is attached to the electron in a wire. So it is attached to the electron in a wire. So what do we see? Force at moving. Okay, this is moving along with the electron. So as it is moving with the electron, so the velocity of the electron that will be experienced in that frame is 0, because it will be moving along with the electron. And we also know that if a charged particle moves in does that move in a magnetic field, then there is no effect of magnetic field on the charged particle. This is because of the V term. Then E plus 0 cross B becomes 0, and this gives you QE in Z direction. Okay, this is force moving. Okay, see, both have force in Z direction, and according to the principle of relativity, the principle of relativity says two things. First of all, that the speed of light is constant in all inertial reference frame, and the second thing that it says is elucidated by Henry Poincare, that the laws of physics are such that we cannot differentiate between inertial frames. So we just cannot differentiate about the moving frame and the rest frame. So the force which we experience here will be equal to the force which we experience there. We will say, you may say that is a magnetic force, and you may say this is an electric force. So we can perform experiments and say about and we can differentiate those two forces and can say that the two frames are different. But no such experiments are possible that can differentiate between this magnetic field and this electric field. We can only know about the magnitude or the force itself and nothing more. We cannot know what is the electric part and what is the magnetic part. We can only use the Lorentz formula and can find the total force, and that is all. We can't distinguish them, just can't distinguish them. So here we see a force that is produced by magnetic field. in the rest frame is equivalent to a force that is produced by electric field in a moving frame. So electricity and magnetism are connected. They are connected. So that was the thought for the day. Now I think everybody have understood it quite nicely. So we'll go a little deeper into realms which are untouched sometimes, but I will give only an overview, but this will be of help to the more esoteric conversation. Okay. The electric and magnetic field are related by a tensor. A tensor is something which has indices. A tensor is something which is indices and which transform according to a certain law. And the law is very close to the transformation properties of x, y, z axis on a rotation. Okay. I will not go deep, and I will only mention the electromagnetic field tensor or the Faraday tensor, and it is given by F mu nu. Okay, first let us start with a normal tensor. A normal tensor in relativity, it is given by T sigma equals L okay, and this thing is something due to Lorentz, and you can calculate it directly from the transformation properties of x, y and z axis during a boost. What is boost? Okay, we'll continue this in another video, but now let us elucidate the electromagnetic field tensor. F nu is given by C 0 plus E x plus E y plus E z minus Ex y minus, because this is an antisymmetric tensor. See that an antisymmetric tensor has only 6 independent components. Rest of them are zeros and negatives. Here will be a 0, here will be a 0, and here 2 will be a 0. Okay, here will be b y bz. Here will be minus by, and here will be bx. And similarly, if there is bz, here will be minus bz, minus by will be plus by, minus bx. Okay, that is enough. So this gives us the electromagnetic field tensor. You can change the tensor signs. You can take those indices upstairs or downstairs and can calculate the different modes of electromagnetic field tensors. But this is something which will give you the transformation properties of electric and magnetic field. How the electric and magnetic field will be different in different reference frames. We know the electric field and magnetic field will be different in different reference frames, but we do not have adequate apparatus that can differentiate between them. So this is more of a theoretical part. You can say that electric and you can say that magnetic. What we experience is the force that is exerted. Okay, now I'll show you the transformation relation. Just like that, it will be equal to F sigma tau. This is in the new coordinate system. You can give it a dash, just like a dash you can put here. Okay, this is given by L F mu nu sigma and tau, and this gives you the transformation properties of the electromagnetic field tensor. And from the electromagnetic field tensor, and after getting the value of the electromagnetic field tensor for electric and magnetic fields, you can compare how the electric and magnetic fields change. Electric and magnetic fields, which we refer to generally, are not as fundamental as they seem. The more fundamental quantity is the vector potential, electromagnetic vector potential, that comes out in the expression for the Lagrangian, the principle of least action, and so and so. Okay, I think I have to end the video here, and I hope you have liked it, and in a comprehensible way you can, by this simple example, show people, demonstrate them that what we say as electric and what we say as magnetic are just artifacts of the coordinates. Thank you.